lunch, sorry, the coffee break lasts a bit longer to let everyone talk. And we now start the second session of today's conference. We have three presentations, and the first presentation is about analysis of community structure of graphs, and the perspective that will be presented by Sebastian Zajac is about how to detect outliers with respect to graph community structure.
Okay, so thank you for introduction and thank you for organizer to be here. It's a very great pleasure for me to speak to you. So my topic will be covered with outlier detection in community structure. So how we can use community structure to get outliers. About outliers, Pavel said that we can have a rare Newton books, it's kinds of outlier. And I also can be here an outlier because I'm not computer scientist and not a mathematician, I'm physicist. So but I don't feel as an outlier here. It's very kind and pleasure conference. So, okay, so what we mean by anomaly detection is just ordinary techniques that we can use to get unexpected behavior, rare events, strange objects, or something called outliers. We know that from statistical point of view, we can check that if we have some data sets that we can produce distribution, and this distribution can tell us if some elements is outlier or not. So it is high probability that is generated from our distribution, or low probability that is generated from distribution. This is pure statistical point of view. But of course, we can use this thinking in other kinds of data, like and other kinds of situation. That outlier could be a situation that not only is somewhere in a different direction or in different place from the data points, but this is individual points. It could be also a graph kinds of anomalies, like label anomalies. It could be something strange in our time series. It could be something strange in text searching, or many different cases. So we know that we can use these kinds of thinking in many cases in the business and in the science. For example, in high energy physics, astronomy, cybersecurity. We have a lot of talks about how to find fake news and etc. This is also connected with this kinds of thinking. So outlier detection, it has a long history. It's nothing new, but of course it's techniques that try reject or find extreme cases. So you can, in practical case, you can use online learning, offline kinds of processing computer for any kinds of data. They could be tabular data, unstructured data, graph data, and what you want. You can use deep learning machineries, machine learning models, supervised, unsupervised. It doesn't matter. We know that this all kinds of techniques you want to use to get good results. You can use CPU, GPU, or even quantum computers to get this modeling faster and get better results. And in our case, I'm interested in how we can find outlier detection in some simple graph. So no dynamic graphs, no something strange, but ordinary simple graph without even without feature for each node. So I'm not interested in the changing a graph to the by embeddings and do a traditional machine learning modeling, but I want just see graph and say, okay, you are outlier, you are not, etc. Okay, so to do this, we can, of course, we cannot do this just looking for a graph beyond of some internal structure, and we know that very important structure in graphs is community structure, that it can help us exploit more our graph and say more about what connections are and which are friends of friends. And we know that there was a full of talks of our conference is about this topic, how the community structure works and how they are realized. So by community structure is just reminding that we understand a set of nodes that can be split into several subsets, but these subsets are densely internally connected. And of course, because even if we have a small number of nodes, there is a lot of partition to consider. So this is a very hard problem, how to choose how many clusters do we have. But of course, we can use to define where cluster is good or not. We can define, I will call it historical approach, that we can define that. Okay. So now I am practical more than physicist. Okay. So we can just say that degree of internal, for each edge, degree of internal connections are more is more internal connection than external connection, and we can define strong community and weak community. So in this picture, we can say that outlier will be a node that does not have most of neighbors in any of the communities. But of course, in this approach, we will need to take too many nodes as outliers. Why? Because it's strictly connected with, there is no dependency on the community size, and so this approach will be not so good to take outliers, but of course this is one of the proposition. So the next step is going to the how we can detect community detection, community structures. We can detect them by something called modularity function. So modularity is based of the comparing actual density of edges inside and density density that we would expect to have in some graphs with some random models. For our example, it will be Chang-Lu null model. Okay, so we can define this modularity. It was defined in our talk. So we have definition that we have something called edge contribution and the grid tags. So this is connected with how the structure of our community is and how we expect to this, how it should be from our null model. Okay, so we know that so we change our problem how to find communities to maximalization of these kinds of function. Yeah, so this is typically like in machine learning and deep learning methodology. Okay, so we know that also that this modularity function is prone to the resolution limit. What it means? It means that if we go to the, if we put some parameter lambda in here, we can take this possibility that if lambda goes to infinity, each node is a community. This is also this is no mistake. This is just outlier. So if you see it, it is okay. If not, it's outlier, it's rare. So as you see, we can modify our modularity function by ordinary way by this parameter. So how is it possible that if I change this parameter, I can find something which I call outliers? Yes, of course. And for this purpose, I take some experiment with some random graphs. And these random graphs, I prepare just one because I want just checked what I suspect some experimental results, and I just checked if this is correct or not. So I prepare a graph with a lower high of noise, with 1000 nodes and this number of edges, and I know that I have in my ground truth 25 outliers. Okay, so I apply a Leiden algorithm with different lambda value, and what makes these outliers is it's it's a degree structure of in the community, not only in the full graph but also in the community structure. Yes, so probably
it's an ABCD.
Yes, yes.
Basically, create edges with a given degree, so degree is preserved.
Yeah.
And it's nothing special about the degree. The edges are randomly generated, meaning we're not paying attention to communities.
Yeah,
your neighbors are sprinkled across the whole graph.
Probably this next slide answers your question that I use a ABCD O version of generator that I generate this graph, and this is a generator when you can you can generate ABC graph like in ABCD, but you have a part with outliers, and these outliers can be also generated here in graph structure. Okay, so I know what is grant true. I take for simplicity I take a low level of the noise, so I suspect that everything should be correct and perfect. And when I do a computation with different level of this lambda resolution, we can check easily that number of communities rapidly grow. It is normal. And if I take this region here near, we can see that if I change the resolution from 1 to the 3, it give me a twice community numbers at the beginning. So this is very, very high high growing. So for comparison, I took yes.
So why there's this
Because we use Leiden methods, and in Leiden methods you you ask about this, yes? Yeah, in the beginning is, but because you have small numbers of nodes that are outliers, and ABCD produce normal nodes for rest of the graph. So probably this is the reason. And here is just implementation of a Leiden algorithm that so in this graph there is no nodes that can construct a next community independently on the best. Yeah, probably yes. But the main result is that you see this how fast is growth. With lambda 1, you have 7 communities. Yes, so this a grant rule also has 7 communities. Yes, from lambda 1 we construct a perfect comparison to the grant rule. So as you see, this set of numbers, what this set of numbers say, it's the first number is label of the community, And the second number is how many outliers I have in community, and how many nodes I have in this community. So you see that everything is okay. I have random numbers of outliers in each in each community. So it isn't that the ABCDO, it isn't that you get a community with just outliers and something. We graph the outliers comes in the you get these outliers in this and in the each elements of your community structure. But if you take this parameter to the 2, we can find that we have 12 communities, and we can see that we have from the last one that we have one community with 1 nodes, and this node is outlier. This is also, we have community with 4 nodes, and these 4 nodes are also outliers. So this is show us that it could be good things that if you change this lambda, you can find small communities, and these communities can be treated as outlier. But of course, there are still they are some outliers connected to the other communities, other higher communities. So in this picture, I just put information because what is wrong with this lambda, maybe not wrong, but what is not good enough with this lambda operation, that if you put lambda too high, you get more and more small communities, and and after that you don't know if they are truly outlier or not. So it is hard to check what kind of lambda parameter you should use to get all your outliers, because of course here I have ground truth and I have artificial prepared graph, so I know everything and I can check, oh, everything is okay, but in true situation it's not so easy. Okay, so our next steps is asking how we can prepare and modify this this modularity function to get this situation that we really separate outliers, which we mean that we really separate small communities and edges that can be constructed with small communities. Do not with the resolution that we do not touch good communities and nodes in the good communities. Yes. So how we can, because modularity function, just the resolution limit problem is that you get many communities, but these communities are large. It is good, but we search how to modify this modularity function that you can find small communities and large, not only small. Okay. So we propose in our work, we propose something, this kind of modification that this notation is that if we want that our community, the number of nodes in our community is less than delta, it is true, and in other case it is false, and we multiply these elements by volume of each community. And we multiply this by some new parameters beta, and as you see, this modification is just on the level of the edge contribution, not for this degree tags. So we do not modify our expectation from models, but we modify elements on this side. So we can say that we have regularized kinds of modularity function. Yes. So, and in a simple case, we take information. We take this parameter delta as 1. So we want to separate just one node community in our case, but we also want to find communities, other communities which are huge communities. So if we put this delta to 1, we can compute that we can take some kinds of beta star score, and this score can be computed for each node. And this is the relation how this score looks like. And so in this picture, we can say that outliers have a low fraction of within community edges, while at the same time moving them to another community does not improve the situation. Yes, so, and of course, we take our outliers as a one node community in this picture. So, sorry? Volume is here I have.
V is number of within community edges.
Yes, this is here. Sorry, I will do it quick.
You don't have it here.
Yes, here is the. Okay. Technicals. This is definition of volume of set I. This is sum of degree of nodes in A. Yeah, because this is for each community.
So E and with subscript V is for this node how many edges it has within community.
Within community AI.
Within community to which it would be assigned if we set beta to 0. So like with original modularity. So in a sense, beta star tells me how much bonus should I give for small communities to decide that this node should be detached from its original community that would be assigned using standard modularity.
Something like an outlier for.
Yeah, exactly. And
this is the reason why I told you that beta star could be kinds of score for being outlier. Yes. And of course, we prepare some experiments for this with ABCDO generator, and we test how this generator and how this score works when we change the noise level from this point to this point. So we want checked in each kinds of level how it works. For comparison, we can produce also something called participation coefficient, and this is also kinds of score for outliers. So we can get these kinds of results that if the noise level is less, we have this the same perfect results for searching outliers. And if the level is more than 0.4, beta star can be search the outliers in better way than this participants coefficient. And okay, and here we see that for very noisy graphs, as we expect, is 0.5. So these two methods doesn't matter what you see, because you say that there is a half probability that is outlier or not. So this is just randomly, you totally random choose outlier of not outlier. Okay, but the interesting result is here that because we take a lot of graphs and we can compute a box plot for our difference between our beta star score and PS score. So we see that in the low level of noisy we have the same results. It is of course good, but in the high level of noisy we have what we expect, that we cannot say that we choose outliers in each methods. But the important thing is here that if you have a graph that is noisy by 0.2, 0.5 to 0.6 you can get relevant information from beta star score, that you can get better information about outliers in this meaning. So this is all I want to show you, and so my talk will be outlier talk, very short. So thank you.